Hi, I am online Wyzant math tutor Joseph Burke, and I'm going to attempt to define for you how you find a plane that is tangent to a surface at a point. So the first thing we need to do, and things I'm going to explain here require a substantial background in advanced pre-calculus and even third semester calculus to understand the explanation. So if you don't understand everything, you might go back and review these things or learn these things before watching the video. Okay, so the first thing you need to do is define the surface. It is a three-dimensional surface. We're going to have 2 points of input and 1 output, giving us 3 dimensions, which we'll call the dimensions x, y, and z is what we'll give for the third dimension, which is our output to the function. Okay, so now that we've defined that, we should probably show an image of what that looks like. And what I can do is I can show you what that image would look like using an application called Geogebra. And here is the Geogebra image for that function. And what we're going to do is we're going to just pick a likely point, and then we're going to try and figure out, well, what plane will travel through that point that's already on that surface and will be what we call tangent to the plane. Tangent to the surface. So that's what I'm going to show you. I'm going to show you how to find what that plane will look like. And I'm going to use Desmos in order to define that. So I'm creating a Desmos screen so I can easily show you the algebra and the calculus behind this. So, okay, I'm sharing my screen now. All right, so here is Desmos. And our function, as I said, is f of xy. It's equal to xy. And we are going to define a plane. We're going to define a plane using and this is going to be a formula from pre-calculus where we've got A, B, and C, which are perpendicular components of a normal vector. And we've got x naught, y naught, and z naught, which are going to be perpendicular, which are going to be coordinates of a point on the surface and the plane. So if you have, specifically, we've got a point where the three-dimensional point, which requires 3 coordinates, that's going to be our x naught, y naught, z naught. And so we need to find something on this plane. Well, if we pick 2 values, I'm going to pick, you could pick any value for x and y and find z just by plugging x and y into this formula up here. I'm going to pick 1.5 for both of them. 1.5 is 3/2, so 1.5 for x, 1.5 for y. If we multiply the 2 together is to find out our z value, our function value, we're going to get 9/4. So that's going to be the point that the plane and the surface share. And then what we need is the perpendicular components of a normal vector for which we're going to use a gradient. So the gradient we use as a normal vector is going to be the partial derivative of the function with regard to x at the point 3/2. Well, just depends on the point you pick, right? So we're going to have also the partial derivative with regard to y, and then -1. So specifically in our case, the partial derivative with regard to x is going to be y. And for that, you need to understand what a partial derivative is to find the partial derivative of this with regard to x. And for y, it's going to be x, and the -1 is just -1. And I chose up here 3/2 for x and for y. And so using this formula, I plug in for y, I get 3/2. Plug in for x, I get 3/2. And I plug in for z, I don't plug in, -1 is -1. So this is our normal vector. So now we're ready to just plug right into our formula that we use to define a plane. And this can actually be shown on many tools, but we saw that A was 3/2, B was 3/2, and C was -1. And we can see that x was 3/2, y naught was 3/2, and z naught we calculated to be 9/4. And that is how you define the yellow, or define a plane perpendicular to a surface. Thank you very much.